inside the glove box over the course of 1,000 hours, and you can see inside the glove box, in fact, there's no change before and after. So if you eliminate water and oxygen almost entirely from the system, then these things are inherently quite stable, which is very encouraging. We've coupled that too to a technique that we've grown quite fond of over the past many years now at NREL, which is this time-resolved microwave conductivity. This is a photoconductance pump probe method, which basically allows you to absorb light and then measure the free carrier density or conductivity after light absorption in the films. And you can see again here, before and after illumination in the glove box, you basically see no changes in the photoconductance of the film over time. So that means that optically and electronically, these things are really quite stable if you eliminate water and oxygen. What we had then done is basically looked at the effect of air exposure under light, and you can see immediately that now in the P3HT PCBM blend we see some photodegradation. This is over the course of 1,000 hours, and remember, of course, that these are in a log scale, so this is actually quite a small linear change in absorption, which is plotted here as the integration of the area under the curve of the absorption spectrum over time. And you can see here, this is for P3HT itself in the light, P3HT in the dark, exposed to air, and then we have P3HT PCBM and in the light and the dark, respectively. And basically what you can see here is that P3HT itself is actually relatively unstable, obviously, to light and oxygen or air. However, when we add the PCBM, we actually effectively stabilize the material or stabilize the system by what we believe is basically a charge transfer and dissociation of that excited state in the P3HT, which is no doubt responsible for some of the photodegradation in the system, but I'm sure we'll hear a lot more about that as the week goes on. And then finally, we have, again, the TRMC data as a function of time for these conditions. But what I want you to take most away from this is more or less that, in fact, in the first 200 hours, where there's very little change in the optical spectrum over that time, you actually see 2 orders of magnitude loss in photoconductance over the first 200 hours of degradation. Again, in the light. In the dark, these things are still relatively stable, but you still lose a factor of 2 or something like that on the order of 1,000 hours. So that's to say that just because you don't see changes in the optical spectrum, for example, that doesn't mean that there aren't substantial degradation mechanisms that are occurring in the active layer. To revisit some of this photodegradation as a function of time, what we can look at is as well changing effectively the energetics between the polymer and acceptor materials. And so this is a study that Matt Lloyd had done with Mike McGee's group a couple years ago now, where we're looking at more or less different polymer materials with different fullerenes and then evaluating the photo-bleaching rate over time. One of the take-home examples here, though, is that some of these systems, as Frederick mentioned, for example, PPV is actually really quite unstable. P3HT is relatively stable, and this is a PCDTBT system, which is actually showing really quite good photostability over time. And basically that these map, to some extent at least, with the ionization potential or the HOMO level in the polymer. And what's also curious is that, in fact, the fullerenes play a large role in this, as you might expect. That's in fact what we concluded with regards to the TRMC data that in the last slide, is basically that some of the photoconductance loss actually is coming from the fullerene as well. And I know there's going to be quite a bit of discussions, hopefully, on the role of the fullerene, because we don't pay enough attention to that component in the system. But effectively, that as you decrease the electron affinity of the fullerene, which often increases the efficiency, at least with P3HT, you actually reduce the photostability of the system and have faster photobleaching rates. So we've kind of continued developing this setup at NREL, largely just so that we can measure now a number of samples very quickly over time. We now have a setup that includes 2 sets of 4 halogen bulb arrays, basically with a CPU fan just to cool everything. And then we have underneath, Matt Lloyd actually came up with this. These are actually just little clock motors, battery-operated clock motors, that we put our samples on that rotate so that we have uniform light distribution underneath there. So we get very uniform photo bleaching of the samples that way. And what you can see here then again is on the left P3HT PCBM spectrum over time. And what I just want to touch on a couple things today. We've been working on this now for a couple of months, and we have a lot of TRMC data, a lot of IR data, a lot of PL and things like this, which we haven't really kind of stitched all together into the story. So I'm just going to touch on the front end of this, which is basically what I just showed you. Is the optical spectrum, again, as a function of time under light exposure in air. What you can see is PTB7 is a very high performance material in the field on the order of 8 to 9%. And in fact, what you can see here is that PTB7, this is the polymer only, is really quite unstable. This line is 24 hours under light illumination, so it's really quite poor. When you add PCBM, you don't actually stable it much, and in fact, it may actually be worse in the blend in terms of photo degradation kind of resistance. And so again, this is the 12-hour line, and you've already almost you've substantially changed the material optically, let alone electronically in the system. So we've been doing a lot of work on the kind of materials design side of this as well, as I mentioned. And so we have a different component. We call this a CTD unit, which is similar to the TPD unit with the nitrogen bridge, but we remove some of the electron density from the system through a carbon bridge between the 2 diones. And then what you have essentially is optically something that looks really close to PTB7, but in fact it's actually quite a bit more stable. So down here we're talking, by the time we get to 24 hours, it's taken an order of magnitude longer in time in order to see the same kind of photo degradation. And furthermore, in the blends, you can see now we have something that at least looks very similar to P3HT PCBM in a much lower band gap system, and these so-called push-pull systems. Obviously, what you can see here immediately is that these are both BDT-based systems. We both have ethyl hexyl alkoxy substitution on the donor unit, and so in fact we don't think it has much to do with this unit at all in terms of the change that we observe here. The degradation that's still occurring here, that's what we're trying to really ascertain as to what's going on. But we can see quite immediately that the thionyl-thiophene is likely responsible for the very poor photo degradation response that we see here. And then over time, if we plot basically the integrated absorption over time, you can see that, again, this is the PTB7 polymer only. This is the blend with PCBM. This is our CTD equivalent, and then with the blend as well, again, you can see fairly good photostability over time. These are all unencapsulated in air under light. So the second part of the talk, I'm going to take a little bit more time and talk a little bit about stability of contacts and device architectures. And so this is more on the device side. As such, we have a combinatorial degradation system. This too was built by Matt Reese now 6-7 years ago. So we've been doing this for some time. Basically, we can hold up to 60 substrates under the same light source. In fact, we just received 2 new light sources, which actually gets us to class AA for spectrum. And we're going to be able to increase the intensity up to 1 sun again, uniformly across the system. Basically, this system otherwise was constrained to about 0.7 suns, and this was an unfiltered sulfur plasma bulb. You can see the spectrum of the emission down below. What's important to note here is all the devices, when they're not being measured, are actually held under load. And so that this is a resistive load. We can change that as we like. But effectively, they're producing power over their entire tenure on the system. So effectively then we have the lighting, the sulfur plasma bulb probably about a meter above the sample stage, and these are all then controlled with electronics or JV measurements. And we can measure these all 60 substrates, each with 6 devices every a minute or so if we wanted to. And sometimes actually you do need to. So if I step back, I just want to touch on the role of contact layers in OPV devices. And so as much of the field is working on the active layer component, the thing to remember is as we change the active layer, we should try to compensate for any electronic changes in the active layer with the changes in the contact as well. So as we drive the ionization potential of the polymer donor, for example, deeper, we need to compensate for that at the whole contact. And likewise, if you're going to lower electron affinity acceptors, or even things like PCBM, we don't really know if we're optimized with our typical electron contacts for those systems yet. We need to optimize for that. So I'm going to talk primarily of 2 device architectures: the standard device architecture, which is largely kind of fed over from the OLED efforts that came before most of us. These must be fabricated in inert atmospheres, largely because you have very reactive metal contacts on the top. In fact, we 10 years ago were making devices on inverted architectures, which I'll show here in a bit. But basically, if you invert the polarity of the device, now you can use more stable contacts for your top, and that actually enables a lot of things, as Frederick talked about, in fact, of printing processes as well, which this entire device stack can and has been printed at Riceau and at NREL as well. So the one thing, or the biggest thing that you can observe between these 2 device architectures is really just very easy to see, that these are unencapsulated, under operation, under continuous illumination. And what you see here is that the inverted device is orders of magnitude more stable than the conventional device. And in other talks that I give, and this community I probably don't need to really mention, but this is obviously where we get our bad reputation, right? And I blame that all on OLEDs, not really on OPV necessarily. And what I'll show you hopefully here is that this, most of this we don't believe yet is actually the organics layer at all. Matt Lloyd had done a while ago with a collaboration with Mike McGee at Stanford, laser beam induced current or a photocurrent mapping experiment, where basically you can see we take P dot versus bare silver on the top of these inverted devices now. You can see very uniform degradation in the silver and very, very non-uniform degradation in the P dot PSS. This could be the result of water absorption in the P dot PSS, thereby changing the conductivity dramatically, or in fact mechanical adhesion issues as well. And the other thing to keep in mind here that we observe is that there's no edge-in decay on the bare silver, but there is edge-in decay in the P dot sample, which again I think either indicates that the P dot active layer interface or the electrode is actually causing problems. So what we think here is we see this initial burn-in, at least in these devices, seems to be the result of edge-in or active area loss in the device. And in fact, if you looked at these in absorption measurements, you wouldn't have seen much of any photo-bleaching at all. And this is some work we've done a few years ago now as well, where we extend or increase the thickness of the silver layer and increase the effective lifetime of these devices, statistically showing that the average lifetime always increases, but you always see this catastrophic failure in devices with P dot PSS on top. And then on the right there, you can see these are, again, unencapsulated devices with a aluminum silver contact, which then allows us to hit time to 80% or T80 values of the original efficiency out past 5,000 hours, again with no encapsulation. If we do encapsulate these things can be really quite stable. Again, as Frederick said, this is a bit unfair because it is glass, but at the same time, these have been under continuous illumination and load, producing power for over a year without any substantial degradation at all. So next I want to just focus in on the contacts here and pay special close to zinc oxide, the active layer contact here. Show you that, again, we've been working on these for quite some time. This is work that Matt White and I had done as PhD students now 10 years ago, making these inverted devices. And we've recently been able to extend this these device architectures so that we're able to address perhaps changes in the energetics in the active layer on the electron acceptor side here, so that we're wondering how we can actually influence the electronic properties of the zinc oxide so as to improve performance and hopefully stability in these devices as well. So what I had done when I was a PhD student now a while ago is alloy zinc oxide with magnesium. Effectively, this increases the band gap, which you can see here. And in fact, if we then make devices with either, this is P3HT PCBM or P3HT ICBA, you can see quite dramatic improvements in the device performance with 10% magnesium. And this has been recently published in Advanced Energy Materials, where we basically are suggesting that this is due to decreased recombination in the cell, partially due to perhaps better energetic alignment at the conduction band active layer interface, and or increased hole blocking in the system. And if we look then at both of these systems as a function of magnesium content, you can see here that around 10 to 15% we're maximizing the efficiency, and the efficiency goes up quite dramatically for these devices with P3HT ICBA, which may make sense because that is a lower electron affinity acceptor. Finally, we have done recently a bunch of degradation studies on this, looking at the effect of magnesium content on the device performance. And you can see here we're stabilizing the device performance as well with about 10 to 15% magnesium. And actually, when we get to 20% magnesium, we've actually seen some other kind of failures that have evolved in the system in terms of these so-called S-curves, which I'll talk about as well. But you can see over time that the 10 and 15% magnesium, actually all of them are more stable than the zinc oxide only. What I'd like to touch now on is the ability to try to modify the work function across that interface between, say, zinc oxide and the active layer. And this is some work that we've published now last year on modifying the work function of ITO directly by the self-assembly of these phosphonic acids on top of ITO. What we can see here is that the work function can change from greater than about 5.4 eV down to about 4.4. This is measured via Kelvin probe, just by changing the dipole in the molecular species here. So we can change the dipole from pointing basically this way to that way. And in doing so, the work function directly influences the VOC in these systems quite dramatically. That's not unexpected because we have ITO underneath. ITO is not a selective contact for anything, so we're actually improving the device performance quite dramatically. If we invert that device now with zinc oxide underneath, we can take these two edges of the study I just showed you, here and here. Basically, this one decreases the work function, which should be a good thing for an electron contact. This one increases it. And in fact, we see the opposite trend now, which you would expect. If we increase the work function of the zinc oxide, the VOC decreases. If we decrease it, the VOC increases. What's interesting here is that there is no S-kink at all. That's introduced by changing the electronic potential or any electron barrier for extraction in this system. And so I think this hopefully informs what we think is going on with these S-kinks. What's curious, though, is we deposit these by spin coating because we can't soak them in zinc oxide. They're acid, so they will etch zinc oxide quite effectively if you leave them exposed. But if you spin coat them, they're actually really quite stable. They bind quickly. And what you can see here is that dilute solution that's been spin coated modifies the work function and VOC as discussed. But as soon as you make that solution thicker, you actually see this S-kink form, which is, I think, a pretty conclusive evidence that this has little to do with an energetic barrier and more to do with a kinetic barrier, so that you can't extract the carriers very quickly. And in fact, you get space charge buildup that causes the S-kink. And I don't know of any real examples that show an energetic barrier that can actually accomplish an S-kink at all. And in fact, you can see this as well with the system that modifies the work function in the other direction. As soon as you get to 10 millimolar concentration, you see that S-kink again. Just to revisit, this does, of course, inform the zinc oxide systems, which require this light soaking to get rid of the S-kinks. And in fact, we can modulate that a bit. Oops. And you can see here that by modifying the zinc oxide, we can actually have these light soaking effects not be removed entirely, but you can make them very, very short-lived, so that we can stabilize these devices very quickly when we modify them, which again gets back to more or less the zinc oxide changing conductivity and resulting in space charge buildup in the system until you actually photodope effectively the zinc oxide. We have some modifiers I've been working on with Alan Sullinger and Jen Braid, who were basically modifying this system to understand how to design the modifiers intrinsically. So this one is basically saturated, so there's no electronic coupling between the acid and the benzene ring. Here we have one that's conjugated. In fact, we see a larger change in the work function here. So this is half an EV change. This one is almost up to 0.8 EV from zinc oxide alone. And you can see, again, improvements in device performance. And I just want to touch quickly on a couple things. I won't go through this. But effectively, we want to look at the role of the zinc oxide in this. And we often use two chemistries at NREL for zinc oxide, both of which we've kind of worked on from the beginning. This zinc acetate dihydrate, which you can see here in red and on the bottom, and then the diethyl zinc on top. The diethyl zinc is annealed at a much lower temperature. We've done that comparison between the two, and these two actually work equivalently. If you anneal zinc acetate at much lower temperature, the devices don't really work nearly as well. So what you see here, though, is if you make these devices, they perform nearly equivalently when you make them originally, but you can see very, very different degradation behavior in the two systems. You get this very large leakage current that is induced in the zinc acetate. And when we modify these now with the phosphonic acid, you can see that you have a large stabilization in the VOC in the zinc acetate when you modify the surface. And then the photocurrent is obviously not really related to the contact itself, which you can see here is independent of that. And then over time, now you can take and see that there's pretty substantial changes in the VOC stability in particular in these systems. And so the functionalization dramatically stabilizes the VOC. And then this is basically my last slide here. Is what we've done is looked at the absorption edge of the two zinc oxides, and you can see that the band gap of the diethyl zinc is quite a bit larger than the zinc acetate. And then if we compare that to the PL emission, what you can see here is that in the diethyl zinc case, the onset of absorption is the black line here versus the peak emission from the near edge emission of the PL. You can see about a 15 MeV change or shift between those two energies. However, when you look at the zinc acetate, this is actually quite a bit larger, about 4 times larger, showing a pretty dramatic shift between the absorption edge and the PL emission, which is indicative of some very shallow traps that might be at the interface. This has been attributed to zinc interstitials. This is in review at Energy Environmental Sciences. Basically, when you modify the zinc acetate with the phosphonic acid, you see now we're shifting back and hopefully removing some of those defects. And you can see, in fact, in the XPS that there is a large emission here in this diethyl zinc case, but that doesn't seem really to affect the device performance or the stability. It's this zinc interstitial that we believe is really causing more of a problem. So with that, I'll conclude, and hopefully I've shown you that the active layer and the contacts all dramatically inform the stability and can control these things quite deliberately. And I'll thank you for any questions.
Questions. Thanks, Dana, for very good talk. Some time ago, we studied devices, inverted devices from Frederick groups with concentrated sunlight with zinc oxide containing for accelerated stability testing, and we found this very strong and fast reversible degradation of zinc oxide. I wonder if you observe something reversible in your zinc oxide and zinc oxide magnesium containing devices. And the second question is, do you conclude that zinc oxide can be stable for OPV? What is your final conclusion?
So to answer your first question, I would say the only reversible effects that we've seen in the devices that we've investigated are these S-kinks. The S-curves are certainly reversible if you expose these devices to oxygen. In the dark, at least, you see the S-kink evolve. We've never really seen them in the light, though, under exposure to oxygen. So I wouldn't say that we've seen anything reversible therein. You might be doing some very different chemistry, obviously, at high concentrations, though, or high intensity light. With regards to the stability of zinc oxide is, we have kind of a love-hate relationship with it. Compared to TiO2, it's much, much easier to process, much more reproducible in our lab. You know, there's the arguments that it's much less stable, and it certainly, if you look at it wrong, it can dissolve. The question there becomes, you know, controlling those kinds of species in the active layer itself. And I would say that, you know, the devices that we have shown over the course of a year or more hasn't shown any degradation that's probably related to zinc oxide yet. So I would say that we're probably fairly stable, and we certainly can control that as well. With either the magnesium, without the magnesium, with the surface modifiers, we've shown, hopefully, that this is very relevant as well.
Okay, thank you. Maybe one short. Yeah, but please keep it short.
Hello, you commented on the photo bleaching of the P3HT and the PTB7 at the beginning, which didn't take place in the glove box but in the oxygen-containing atmosphere outside. Is there a common agreement on what is happening chemically to the molecules? Could you draw the chemical formula before and after the photo bleaching?
I could, but honestly, I think our next speaker will probably have more intelligent things to say about that, so I'll just leave it at that. But certainly, I hope that we can discuss that during the meeting, absolutely.
Okay, thanks. I guess Dana is around for more questions in the break.